Hello, my name is Eduardo Villaseñor and I am going to talk to you about our paper titled Two-Dimensional Kicked Ising Model, Dynamical Phase Transitions. Many body quantum systems are in these days one of the most exciting fields of physics, mainly because of the difficulty to study them from both a numerical and a mathematical point of view. In this paper, we analyze a two-dimensional spin system characterized by an Ising interaction and a modulated magnetic field. To show our analysis, we tell three different stories: by observing the level density, the level spacing distribution, and by measuring correlating functions of global observables. First, we are interested in the transitions between a flat spectral density and a spectral density with a shape essentially dominated by a single Fourier component, as they are associated with regular and chaotic dynamics correspondingly. The first results show how for different lattice sizes the spectrum behaves in a stable manner, and this also holds for different symmetry sectors. Doing an analysis, we see how in the integrable regions there is a main Fourier component dominating the shape of the spectrum, in contrast with the places that show no sign of integrability, where we see there is no such dominance, as all Fourier components are all close in magnitude. Over the parameter space, this allows us to find the regions where a flat spectral density is present for different lattice sizes. For the level spacing distribution, we analyze the commonly studied nearest neighbor distribution. That is, we consider the distribution of the separation of the neighbor energy levels. The results show in almost all cases the distribution is described by the Wigner-Sormeis, with the exception of the trivial integrable cases of zero magnetic field or zero spin interaction. Finally, we focus on dynamical correlations of local observables. Considering a traceless observable M, we define its time autocorrelation with respect to the kicked Ising dynamics as this function. By definition, the observable is ergodic with respect to the dynamics if its time autocorrelation vanishes to zero over long times. Otherwise, we say it's non-ergodic. For the case where the observable corresponds with the X component of the magnetization, we found three qualitatively different types of behavior of the autocorrelation. For small values of the magnetic field, we found there is no decay, neither for large times nor dimensions of the system. An intermediate behavior appears as we increase the magnetic field. This shows an algebraic decay of the correlation to an asymptotic value which decays with the system size. Finally, there are parameters in which the decay is exponentially fast, and again, the asymptotic value decreases with the Hilbert space dimension, suggesting that it vanishes in the thermodynamic limit. A full analysis is made over the parameter space by taking correlation averages over large times in order to understand the transition from ergodic to a non-ergodic dynamic. Over the three different stories we told about the dynamics of this two-dimensional system, we found surprisingly that if we compare the level spacing or the level density diagrams to the one of the dynamical susceptibilities, there appears to be no direct point-to-point correspondence between different regimes. One can have a flat or non-flat level density in either ergodic or non-ergodic regime for the dynamics of local observables. This conclusion calls for a deeper understanding of the role of locality of observables and long-time dynamics. Thank you for watching. I hope you enjoy our paper.